Hi, welcome to our PRML course project presentation. In this, we'll explore how machine learning can optimize the critical process of VLSI circuit partitioning. Let's begin. Firstly, let's analyze our problem statement. What is VLSI partitioning? Very large scale integration involves designing integrated circuits by combining millions of transistors into a single chip. Partitioning then divides the circuit's elements into smaller chips. The objectives are to minimize edge cuts between partitions, balance power consumption and area, reduce critical path delay, and then optimize the wire length to minimize signal delays and power dissipation. Now, classical ML models can help us here by identifying patterns in graph structures and optimizing partitioning decisions, offering more flexibility compared to traditional heuristic based methods. My project workflow was something like this. First came graph generation with attributes like power area and wire count. Then came pre-processing where extraction of features such as node degree and power happened. And then we normalized these features to ensure uniform scaling. Then came modeling where we applied classical ML models to partition the graph actually. And finally came the analysis and comparison part where we evaluated these models on certain metrics and then compared performance and runtime and scalability. The graph and netlist generation part happened, which comprised of nodes and edges. Nodes represented the components like gates and flip-flops, and edges represented the wires connecting the components. The graph types included input nodes, output nodes, and internal nodes. The graph generation was a random process and it ensured realistic constraints such as degree distribution and power balance. Moving on, we implemented a variety of classic ML models and let's see each one of them. First came k-means clustering. K-means was chosen as a baseline unsupervised method due to its simplicity and speed. We projected multi-dimensional node features into a single dimension using average edge distance and then chose two partitions. This method offered quick partitioning and often gave reasonable cut counts, but it ignored the structural and topological details of the netlist. Then came agglomerative clustering, where it follows a bottom-up hierarchical approach, where each node starts as its own cluster and is merged iteratively using linkage methods. Linkage methods like word linkage and average linkage. This method produced compact clusters with minimal cut edges owing to tight intra-feature similarity. Next was spectral clustering, which was our best performing model across all key metrics. It leverages the graph's global structure by using the Laplacian of an affinity matrix. This matrix that we construct using the formula given here. This method captures both local connectivity and edge weights, yielding visually coherent partitions. Moving on to logistic regression, it was another supervised classification model trained on pseudo labels generated by k-means. It offers fast inference and interpretable coefficients, which was useful for understanding the feature impact, and it performed better than k-means. Finally came support vector machines. This was a balanced performing model across all key metrics, trained on the same pseudo-labeled dataset, and where we used four node features like power, area, degree, and average edge distance. We used a radial basis function kernel to capture the non-linear decision boundaries. Now, the metrics that we use for evaluation, which we already talked about, were edge cuts, total wire length, and critical path delay. Another metric, partition balance, is something that we have included in our future scope. Now, our scalability analysis evaluates model performance as graph size increases. We observe that critical path delay increases with graph size, which is expected due to the longer signal propagation paths in larger circuits. Then came our density analysis, where we divided things into sparse graphs, medium density graphs, and then dense graphs. It studied the effect of graph connectivity on partitioning metrics. We found that denser graphs led to fewer edge cuts but higher wire lengths, creating an important trade-off in the partitioning process. Finally came our comparative analysis, where it revealed that spectral clustering achieved the best balance across all metrics as shown in the table, though at the cost of higher computational complexity. Agglomerative clustering offers the best runtime, sacrifices accuracy in edge cuts and critical path delay. Finally, to conclude, our project successfully demonstrated the application of classical ML techniques to VLSI partitioning, with spectral clustering emerging as the most effective approach. Our future work can explore deep learning approaches like graph neural networks, which can better capture the complex relationships in VLSI netlists. Additionally, hybrid models combining classical ML techniques with more heuristic-based refinement would certainly offer much improved performance. Thank you very much for listening to our presentation. Thank you.